Hello everyone, in this video we're going to be looking at section 8.8, which is improper integrals. The definition of a definite integral from a to b of f of x requires that the interval from a to b be finite. For example, no negative infinity or positive infinity as our limits. The fundamental theorem of calculus, which allows us to evaluate definite integrals, requires that f of x be continuous on the closed interval from a to b. Integrals that have either one or both of the limits infinite, or that have a finite number of infinite discontinuities on the interval from a to b, are called improper integrals. In this section, we're going to be solving those improper integrals. Okay, so let's look at the first type of improper integrals. The improper integrals that have infinite limits of integration. In other words, have an infinity on the top or lower limit. So if f of x is continuous on the interval including a to infinity, then what do we have? We have that the integral from from a to infinity of f of x dx, it can be evaluated by taking the limit as b goes to infinity of the integral from a to b of f of x dx. So in other words, if I want to find an integral with infinity as my upper limit, then I can replace it with the variable b and then take the limit as b goes to infinity. All right, so this is giving us a method for how to evaluate these integrals. If f of x is continuous on the interval from negative infinity up until b, then the integral from negative infinity to b of f of x dx can be solved by looking at the limit as a goes to negative infinity of the integral from a to b of f of x dx. So a very similar manner. Now, if f of x is continuous on the whole interval from negative infinity to infinity, then if I want to find the integral from negative infinity to infinity of f of x dx, I can, and the way I can do that is by looking at some intermediate value and finding splitting up the integration from negative infinity to that intermediate middle value, and then adding that to that middle value to infinity. In other words, splitting up our whole our whole interval. And if I do that, then each one of these can be solved by 1 and 2. Right? Notice that 2 is going to be the limit as a goes to negative infinity of the integral from a to c of f of x dx, plus this one is going to be 1, so the limit as b goes to infinity of the integral from c to b of f of x dx. So if we're looking at negative infinity to infinity, I can split it up into two different integrals. That's just properties of definite integrals for some intermediate value c, so I can go from negative infinity to c plus from c to infinity, and then I can treat each one of those like definition 1 or 2. Right? So I'm able to find the integral from negative infinity to infinity. In the first two cases, if the improper integral converges, in the first two cases, the improper integral converges when the limit exists. Right? So if I want to find that improper integral, I look at the limit. If the limit exists, then we say that integral converges. If the limit does not exist, then we say that that improper integral diverges. In the third case, notice that I have two different limits. So if one of those limits does not exist, then the whole thing diverges. If both of them exist, then the whole integral converges. Okay, so let's look at our example here. We want to evaluate the integral from 1 to infinity of 1 over x dx. So in the back of our mind, let's think about what this looks like. Right? 1 over x would look like this on one side and then this on the other side. Right? But we're concerned about from 1 to infinity, so we put 1 like right here. So in other words, we want to find this area underneath the graph from 1 to wherever. So the question is that a finite area Or does that graph, that purple graph, not ever get close enough to the x-axis in order to make that finite? That's essentially what we're trying to find here. Okay, so by the theorem, what we can do is we can say, okay, the integral from 1 to infinity of 1 over x dx, that's the same as the limit as b goes to infinity of the integral. I like to put those brackets around it to remind me that I need to evaluate the integral first and then take the limit. From 1 to b of 1 over x dx. So then I just solve this integral just like I know how to solve integrals, definite integrals. So the integral of 1 over x is ln of x. I'm going to evaluate that from 1 to b. Again, b is just a variable. So limit as b goes to infinity, and I get ln of b minus ln of 1. Ln of 1 is 0, so I get the limit as b goes to infinity of ln of b, and we know what is the natural log function, right? So let me write what this function is so we don't get confused here. This was f of x equals 1 over x. The natural log function just keeps growing greater and greater. All right, so if I were to draw the natural log function, it looks like this. All right, this is f of x equals ln of x. So as x goes to infinity, this also goes to infinity. Right, as I go this way, my graph keeps growing that way. So in other words, this limit is infinite. So since the limit is infinite, this integral diverges. Okay, so now we do another one. Let's look at the integral from 1 to infinity of x squared. So if I look at the integral from 1 to infinity x squared, in this case, my graph ends up looking very similar to the 1 over x, but it's actually a lot closer to the x-axis. And it would look like this on the other side, but again, we're not really concerned about that because we're going from 1 to infinity. Right? So it looks very similar to the previous example, except it's much closer. So just to illustrate this for you, if I look here, if I have 1 divided by x and 1 divided by x squared, notice the green graph, which is 1 divided by x squared, is much closer to the x-axis. In other words, it's much tighter. So maybe it has a better chance of bounding this area from 1 to infinity. Right? Maybe this one can actually converge. We'll see. Okay, so the integral from 1 to infinity of 1 over x squared dx is equal to, by our theorem, the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. Remember, 1 over x squared is the same as x to the negative 2. So I get the limit as b goes to infinity of negative x to the negative 1, evaluated from 1 to b. So that's the limit as b goes to infinity of, I'm just going to write negative 1 over x from 1 to b. So the limit as b goes to infinity of negative 1 over b minus negative, in other words, plus 1. Now, when I take the limit as b goes to infinity of negative 1 over b, I get a really big number in the denominator. In other words, this term goes to 0. So my limit is equal to 1. What does that mean? That means the integral that we were looking at converges to 1. So in fact, like I was saying before, the graph, the purple graph of f of x equals 1 over x squared does end up getting close enough, really, really tight to the x-axis to actually bound that area so that it's a finite area. All right, let's look at another example here. Evaluate the integral from 0 to infinity of e to the negative x. All right, so e to the negative x, that again looks like a downwards exponential function. Oops, wrong things, guys. There we go. E to the negative x right, it looks like that. Oops. Wow, I'm really struggling, aren't I? So it looks like this function right here. So again, the question is, does this get close enough to the x-axis to bound this integral? Right? Bound this area, which is the integral. All right. So the integral from 0 to infinity of e to the negative x dx is equal to the limit as b goes to infinity, the integral from 0 to b of e to the negative x dx. So I get the limit as b goes to infinity of negative e to the negative x from 0 to b. And just so we're able to really see what's going on, remember that e to the negative x is just 1 over that. In other words, this is negative 1 over e to the x, because that negative exponent puts in the denominator, evaluated from 0 to b. So here I get the limit as b goes to infinity of negative 1 over e to the b minus negative, so plus, and then e to the 0 is 1, so this is just plus 1 there. And now, once again, I'm putting a really big number into the exponential function, so that means this denominator is getting really, really big, which means the whole thing goes to 0. Right? This piece goes to 0. So this limit is just equal to 1. So once again, the integral converges to 0. Okay, so as you can tell, these improper integrals essentially just boil down to looking at limits, right? And one thing we should have learned maybe in Calc 1 was L'Hopital's rule. And L'Hopital's rule allows us to find limits, right? So what does L'Hopital's rule say? It says if we have the limit of f of x of some rational function f of x over g of x, and I look as the limit as x approaches c, and I get 0 over 0, or positive infinity over positive infinity, or negative infinity over negative infinity, then I can take the limit of the derivatives over top of each other, right? So in other words, if I want to find this limit of the regular functions, and I end up getting 0 over 0 or infinity over infinity, then the limit of the derivatives of those functions is how I can find the original limit, right? And that makes it a little bit easier. So hopefully you guys remember that from L'Hopital or from Calc 1. Okay, so in this example, my function is 1 minus x e to the negative x. So 1 minus x e to the negative x. What does that function look like? It looks like this, right? So again, you can see if we're looking at the integral from 1 to infinity, it looks like that area might be pretty well bound. So it looks like we might have finiteness, but let's see. All right, so the integral from 1 to infinity of 1 minus x times e to the negative x dx is equal to the limit as b goes to infinity of the integral from 1 to b of 1 minus x times e to the negative x dx. Okay, so first thing we notice here is in order to solve this integral, we actually need integration by parts, right? So let's find that integral first, and then we can plug in our limits for our definite integral, and then we can look at the limit, right? So first, with no limits on there, I don't know why I put a negative 1 here, we get 1 minus x times e to the negative x dx. So I need to pick my u and v. So u is going to be 1 minus x. dv is going to be e to the negative x dx, right? So now I get du is equal to negative 1 dx, or in other words, negative dx, and v is equal to negative e to the negative x. So integration by parts says uv, or 1 minus x times negative e to the negative x minus the integral of u dv. So I get negative e to the negative x minus dx. So this becomes negative e to the negative x plus x e to the negative x plus, minus, because there's 3 negative signs, minus, and then we want the integral of e to the negative x dx. So I get minus e to the minus x plus x e to the negative x minus, and then minus e to the negative x plus c. So this is a minus, this is a plus, so those are going to cancel out. And I'm left with x e to the negative x plus c. So that was what my integral was. So now let's go back to our work here. All right, so that's equal to the limit as b goes to infinity. And now it is our definite integral. So our antiderivative was x e to the negative x, and we're going to evaluate that from 1 to b. All right, because the definite integral just means the antiderivative, which is what we just found, and then we plug in our limits. So now I get the limit as b goes to infinity of b e to the negative b minus x e to the negative x, or minus 1 over e. All right. So let's rewrite this just so we're on the same page here. I get b over e to the b minus 1 over e. Okay, so now we need to, as another side note, we need to evaluate this limit. Right? So I need to evaluate the limit as b goes to infinity of b over e to the b. Right? I'm kind of doing it off to the side here. So I notice if I plug in an infinity, I end up getting infinity over infinity. Right? Which means I use L'Hopital's. So what do? I take the derivative of the top and bottom. The derivative of b with respect to b, here's b as my variable, is going to be 1, and the derivative of e to the b is e to the b. So now when I look at the limit, my denominator gets really, really big when I put infinity in there. So 1 over a really big number goes to 0. So that limit is 0. So now we get this limit as b goes to infinity. We found that this was 0. Whoops, I guess I'll just repeat this. B over e to the b minus 1 over e. We found this to be, this was 0. That was our side work, and then it's minus 1 over e. All right. Why the minus sign? Well, notice this area was underneath the graph, right? That's why it's minus. All right, so the integral converges. So this was a good example because in one case, in order to do the integral, we had to do integration by parts. So that was good practice. And in order to find the limit, we had a hard limit and we had to use L'Hopital's rule. All right, so let's look at another one here. Let's look at the integral from negative infinity to infinity. So notice that if I look at the function 4 over 16 plus x squared, I'm not having any discontinuities, right? No matter what value I plug in for x, the denominator is always going to be greater than 0, right? It's not going to be equal to 0, which would make it discontinuous. So note that this function is continuous on that whole interval from negative infinity to infinity. So what I'm going to need to do here is pick some intermediate value. oftentimes 0 is a really good intermediate value, and break this up into two integrals and then look at the limit just like I did in the previous examples. All right, so in other words, I look at this, I say, okay, the integral from negative infinity to infinity of 4 over 16 plus x squared dx is equal to the integral from negative infinity to 0 of 4 over 16 plus x squared dx plus the integral from 0 to infinity of 4 over 16 plus x squared dx. And now each one of these integrals I can solve with the limits just like I did previously. So first let's look what 4 over 16 plus x squared looks like. So 4 divided by 16 plus x squared. So that looks like this graph. So it has a nice little bump at 0, but it's pretty tight. And so even though we're looking at it from negative infinity to infinity, it looks like it might have a nice finite area, right? It's really close to the x-axis. Okay. So we look at both of these individually, right? So I look at the limit as here we'll go goes to negative infinity of our integral from a to 0 of 4 over 16 plus x squared dx, and then plus the limit as b goes to infinity of the integral from 0 to b of 4 over 16 plus x squared dx. Okay, so now we got to evaluate each one of these integrals, right? In the back of our mind, we see something plus something in the denominator, we start thinking about tangent, right? So we can pull this 4 out front because it's just a constant. So the 4 will just be out front. And then we remember the tangent rule, right? So the tangent rule is, remember off the top of my head, it is the integral of 1 over a squared plus x squared dx is equal to 1 over a tangent inverse of x over a plus c. So that's the rule that we're going to use for these integrals, right? And remember the 4 gets to hang out for the ride because it's a constant. So the limit as a goes to negative infinity of 4 hangs out for the ride, and then I get 1 over, what's my a in this case? What am I squaring to get 16? Well, that's 4, so 1/4 tangent inverse of x over 4, and now I'm evaluating that from a to 0, and then plus the limit as b goes to infinity of, again, 4 hangs out for the ride, and then I get 1 over 4 tangent inverse of x over 4, and I got evaluating that from 0 to b. All right, so that was the rule, and now we will simplify. So my 4's cancel out with each other, so I'm left with the limit as a goes to negative infinity of tangent inverse of x over 4 evaluated from a to 0 plus the limit as b goes to infinity of tangent inverse of x over 4 evaluated from 0 to b. Okay, so limit as a goes to negative infinity. If I plug in 0, tangent inverse at 0 is what I would get here, minus tangent inverse at a over 4, and now plus the limit as b goes to infinity of tangent inverse of b over 4 minus tangent inverse at 0. Okay, so tangent inverse at 0 is just 0. Now I need to look at, this ends up becoming the limit as a goes to negative infinity of negative tangent inverse of a over 4 plus the limit as b goes to infinity of tangent inverse of b over 4. Okay, so now we need to know something about tangent inverse, right? And so what does tangent inverse look like? Tangent inverse looks like the following. I'm going to write it as arctan in here because I think that's the way they like it. So arctangent of x looks like this function, right? And it actually has horizontal asymptotes at pi over 2 and negative pi over 2. So in other words, the tangent inverse function looks like this, and it has horizontal asymptotes at pi over 2 and negative pi over 2. All right? So what does that mean? Well, that means when I look at this limit, when I plug in negative infinity to a over 4, right, this is basically tangent of x over 4. Well, the x over 4 doesn't affect what the tangent inverse does. So in other words, when I take tangent inverse and I plug in negative infinity, when I go all the way over here, negative infinity, I would go to negative pi over 2, right? So I get negative because of this negative sign right here, and then that limit is negative pi over 2. Because at the far left, my tangent inverse graph goes to negative pi over 2. And then now, on the other side here, when I go to the limit as b goes to infinity of tangent inverse of b over 4, what that's saying is I can put that limit inside of the tangent function again, and the limit as when I go to the far right of this graph is pi over 2, positive pi over 2. So I end up getting pi over 2 plus pi over 2, which is pi, which is finite, right? So the integral converges to pi. Okay. All right, we'll go ahead and end this video here.